Okay, I'm going to consider alpha which maps G to H in such a way that alpha of x, y equals alpha of x, alpha of y. I'm going to consider the group G to equal z under addition, so it's just normal integers plus positive or negative integers. H is going to be addition modulo 2 on the set 0 and 1, I guess. So it looks like this: 0, 1, 0, 1, 0, 1, 1, 0, addition modulo 2. Okay, so what's alpha going to be? We've got alpha of x, where x is an integer. And I'm going to specify that alpha of x equals two values: 0 if x is even, and 1 if x is odd. Every integer is either even or odd, and if it's even it goes to 0, and if it's odd it goes to 1. So we better check that it is a homomorphism. How do we check that? Well, we write out the definition. Observe that when I'm thinking about checking stuff being a homomorphism, I just write out the definition of a homomorphism, and then I think, can I do those things? Well, that's what it says. That's what the textbook definition is, but what it means is this: x and y are in my group G, which is the integers under addition. So I'm going to put that there. Equals alpha of x combined group-wise with alpha of y, but the set I'm mapping it to, H, is addition modulo 2, or the group is addition modulo 2. So that's what this is what it says, and this is what it means. So x and y can be even and odd, or odd and even, or odd and odd, or even and even. I'll just do it for one combination and you'll see how the others follow. I'm going to say x is even and y is odd. So actually I'm just going to put a question mark there because I'm verifying it for the moment. I'm asserting that, and I'm wondering, I'm asserting this relationship here, and I'm going to check it. So let's work out what the left hand side is. Well, that's alpha of x plus y equals alpha of, and we know that x is even and y is odd, so it's even plus odd. And I'm sure you know that that is alpha of odd, because even plus odd is odd, of course, which equals 1. That's what the left hand side is equal to. That's this thing here. What's the right hand side? The right hand side equals alpha of x plus modulo 2 alpha of y. That's what the right hand side is. That just follows from the definition of a homomorphism, and we're just going to evaluate the right hand side. It's better be equal to 1, because if it isn't, I've made a mistake. Well, that's alpha of even addition modulo 2 alpha of odd equals 0, because alpha is by definition, there it is, alpha is 0 if x is even, plus modulo 2 1 equals 1, which is what we wanted to show. We wanted to show that these guys are equal, so the left hand side was equal to the right hand side. Now I've only checked one of the 4 cases here, but you can see that they all follow through. So we've actually got quite a lot of information about this group here. We actually know quite a lot about that through this map alpha, which maps to addition modulo 2 on the set 0, 1, which is this even odd business. So what we mean is, what we have learned is that built into Z, we've got this structure about even numbers and odd numbers, and the reason that that's right, the reason that you know it, the reason that your brain has got this information built in, is this homomorphism alpha, which you use almost without thinking. What we've done really is formalize something that we kind of know about Z. But we'll see other examples later on where it's knowledge that we don't really have implicitly, but thinking about homomorphism brings out structure in groups. I'm going to stop there.